Okay, see, today we are going to talk about motions or ship motion. Let me just write motions. Actually, although we are calling motions, it could be any response. What I mean is this, see, we have seen in the past lectures that irregular waves can be finally represented by means of a wave spectrum, okay, and this is nothing but a sum of regular waves. So, I know my environment that I have talked in last two lectures. So, my next question, which is the pertinent question, is I put my ship in that wave, how does it respond? So, here I mentioned it as ship motions, but let me understand or let me clarify that this will apply to any response. For example, it could have been pressure at some point, it could have been acceleration at some point, it could have been bending moment in the midship, shear force at some location, etc. Any response, whatever output that comes out, whatever you want to measure for putting the ship in an irregular waves, how do we get it? This is the question we are asking now. Okay. Obviously, this is most important because our interest is not describing irregular waves. We have described it only so that I can find out how my ship would behave in that. That is my purpose. Now, let us, so we are going to talk about this procedure which is called spectral procedure. Now, let me look at it. First, we are going to look at a simpler case. We will consider a floating body or a ship, you can call, with 0 forward speed right now, just for simplicity of the expression, which means that we are not considering something moving forward because that takes one more modification which will come in a minute. Now, let's take this example. I have this wave and I put a body. Now, I am measuring its hip motion. I have a stick, I measure hip motion. How will it look like? Well, if you take the response z, see, this is wave, and if I take the hip motion, let me call it hip motion or zt, it is also going to look like a random, naturally, because random input is going to give me random output. So, this also I can exactly same way synthesize, I can exactly same way as what we have done in wave, say that it consists of number of sinusoidal waves and end up representing a spectrum for z against omega, which will look something like that again. Because after all, if I look from a different point of view, this is another random signal, whether you call it zt or eta t does not matter. I have a random signal, and the random signal or irregular signal can always be processed and can always be represented in terms of spectrum. So, this I can get. In other words, if I have only this signal to start with, somebody gave me this signal and I am told that you represent the signal, I can always do that. But of course, the fundamental question is, how do I get, given this I get this? That is the question to us. The procedure, given my irregular waves, how do I get my irregular response? This is the question we are asking. But I wanted to tell here is that I can always get this to this. Now, see, there is a very simple procedure and very interesting and nice procedure. Now, let us take one simple example. Well, we are talking of motion, so I will take a sample as heave motion. Now, see, let us say I have a wave, particular wave one frequency wave, eta 1, or say, well, I will put that 1 later on. So, it is given by A cos omega t minus k x, let us just put it this way, or even I can put a beta if I want. Now, this wave gives me a response. This wave is some kind of a sine wave, it gives me a response z. It is expressed as a amplitude into, let us say, cos, let me call this beta wave, beta z. This we have done before, isn't it? We have always seen that in a regular wave. Well, when we talked about single degree freedom system earlier, what we have found out, in a regular wave my response is also regular, it is sinusoidal. In other words, if eta was in this case looking something like this with an amplitude A, my heave here would have looked something like, say, with amplitude ZA. Okay. We have always said that, and of course, what we could represent this as, going by this, I can always call this as ZA by A multiplied by A I can call like that, just in what is ZA by A? Amplitude of heave per unit amplitude of wave. Okay. Okay. Now, obviously, for a given wave of given frequency, this is the frequency omega. Okay. What will happen? My ZA will remain constant, ZA and beta Z. So, that means these things become a function of omega. So, what is happening for a given wave, regular wave, you take a wave of length 100 meter, which would be having a given omega. So, what would happen for that omega, if I put my shape, it is going to have a response amplitude some value. So, obviously, ZA is a function of omega, and so is beta Z. Explaining on, right. See what is happening now. Let us take one particular wave of some length, say 100 meter long wave. Okay. I put my ship there, it responds, say wave height is 1 meter for that. So, it will go up by say 2 meter, ZA is 2 meter. Now, if I have 3 meter, then it will be 6 meter, because in that particular wave of given frequency, my response is linear, because as I said, 2 1 meter wave is equal to 1 2 meter wave. Okay. So, ZA by A is constant, that we know. My point here was to say that ZA is a function of omega. Why? Because it is very common physics. If I have a 100 meter long wave, the amount it will move up and down is not going to be same when if I give a 200 meter long wave, or if I get a 50 meter long wave. I give an example in a minute. Suppose you have this large ship. Okay. So, I have a very small wave, very small omega, let us say. So, what happened? It has a heave for this omega. This is going to some number, but now if I put the same shape under a much longer wave of same height A, same A, do you think that this will be same? Of course, it will not be same, because it depends on the wavelength. So, therefore, ZA by A obviously is a function of omega or wavelength. Okay. In other words, what is happening is that for a given wave of frequency omega, I have an output heave of amplitude ZA and phase beta Z. Obviously, the output depends on the input, and here the Number one is that output per unit of A remains constant, because as far as A is concerned, see here, if I have eta 1 A cos omega t, eta 2 is A2 cos omega to t, I can add A1 plus A2. Amplitude can be added at the same length, but length side obviously the response will depend on omega. So therefore, ZA by A is a function of omega. Naturally, different wavelengths would give you different response. This is exactly what we have done. In fact, to say this, there is a more interesting way of putting that. If you remember our regular wave response, what did I find out? Omega versus, you remember, omega versus here I have got this Z, and how did it look like? Obviously, the very graph showed that the output, how much it responds, depends on omega. So there is no like question or doubt on that fact, you see. So this ZA by A is my amplitude of response by amplitude of incident wave, which you can call transfer function, or I can call this to be, say, some function h. Obviously, it is a function of omega. I can call it because what transfer function essentially implies output by input, right? Yes, output by per unit input, but it is a function of omega. That is what I was trying to tell here. Okay. Now, we will come back to this. This we have discussed several times when we talked about response in regular waves. This is what we have talked at the very beginning, you know, single degree freedom equation, etc., etc. For example, obviously, if omega you know, matched with the natural period, then you would expect ZA to be very high. If it is very far from natural period, you would expect ZA to be very small. Therefore, ZA is a function of omega. It depends on what, you know, wavelength is there. But the question we are talking today is, of course, motion. We are talking of this subject, motion in irregular waves. So what is happening now? This is the most interesting part. See here, I will draw it in a different way. Now I have a incident wave, okay, of this omega 1. Let us say this is omega 1. It will give me a response of the same omega. So I have eta here, I have Z here. Now I take another one. See here, remember this thing. Irregular wave, what we have said in an irregular wave? An irregular wave is a sum of sine curves. So I have started with this, and I say that this is nothing but basically either I can add this to get this, but to start with, in fact here I started with that and I said this is actually sum of this. Now I broke it down. Now each one of them is going to give me a response here. So this gives me this of the same frequency. So if I draw a line here, this is going to give me this response. So if I add it up, I get. So what I am saying, therefore, see, the interesting part is very simple, that this I have to predict this from this. See, I have to predict this line, this red line, which is my response output, which is my Z in t. This is actually my ZT, that is my how it is heaving in irregular wave for this eta t. That is what I have to predict. The question I am asking you is that given this, what is this? Now I have seen that this is nothing but sum of this, which I have done by spectrum. So what I do, I break it down to this sum. Now remember, the response are linear. So this one and this one, that is, if I call this to be here, you know, like any response amplitude here A omega, and well, A, let me call it only A, and here I calling ZA. ZA omega, my ZA omega by A is constant for a given omega, that is linear. So what is happening therefore is that, see, First of all, I will tell the formal procedure in a minute, but you must get in your mind very strongly the concept behind it, the physics behind it, because afterwards you will find out the application is pure algebra. There is nothing much to it. Once you get the concept of how it is, the responses can be done, you will find out that the procedure is algebra. In fact, I am very fond of telling this line that the first paper which proposed the method of determining response in irregular wave, it was called something like motions in confused sea. And I am fond of telling that there is absolutely nothing confusing in finding motion in a confused sea, because it is a pure algebra. But you have to get that idea first. That is what I am trying to spend the time on. So you see, it is very simple. I am breaking it down to the sine waves. Each sine gives me a sine output. This output by input, if I were to draw, this diagram did not come properly. If I were to draw a block here, I will do that in the next graph. If I were to draw a block here, it passes through this, like this to this, let us say, is a black line. That means this multiplied by something gives you this. See, for example, ZA, we have seen this, ZA is ZA by A into A, that is H omega into A. So this is my H omega. So A into H omega gives me ZA. Straightforward. So I can pass it through this, get this. So each one gives me this output. So I have broke it down this way, got this output, sum it all up, I get this line. So it's like I had a black box where I had this, I shook it out, all this filtered out. For each one I found out the response, put this block number 2, again shaken them, I get this out. So you see the procedure, how simple, pure algebra. So getting here, breaking it down here, the only hydrodynamics is in this black line. What is the black line? Find out how much it responds in a regular wave. That is it, nothing else. This part is algebra, we have seen, this part is algebra. So you see, this is confused sea and this is motion in confused sea. This is motion in regular waves. So you see, there is no confusion as far as confused sea is concerned, you are simply adding it. What is difficult is this part, going to the black line. So now, having said that, we will come to another graph. Now it is like this. Response, again we have found out, let me draw it this way now, this is easier to draw probably. We have seen that this waves gives me but what has happened that I have represented this in terms of a spectrum. Remember, this I represent in terms of a spectrum. What did I do? I plotted here this, and actually any point here happens to be half of A square divided by d omega. That is what we have done, isn't it? This is what the definition. In other words, what we have done, see, this I represent this way, but now what has happened, I have an output here. So each one has given me this output. So as far as representation is concerned, this also I can plot in this way, where I have this equal to half of ZA omega square by d omega. Same thing. After all, ZA omega is the amplitude like A. What we do is that we put, this is how we can call it to be SZ omega versus omega. What I am trying to say therefore is that, see, I know how to get from this. See, this goes to this H omega. This black line is that filter Z H omega, which is equal to ZA omega by A, the amplitude of response per unit wave amplitude. This is this line. So it goes through I break it down this way, go through this way, add it up. That this part we understood. Okay. So, this part is I can call response in regular waves. This is simply algebra of breaking down irregular waves into sine components. This is simply getting the output sine components, add it all up to get this. All right. I will tell the procedure in a minute, but once again I am emphasizing that understand this physics. Now, okay, I know now how to get from here to there, but I obviously do not want to plot the graph like that. How did I represent this? I represent this in terms of a spectrum. I do not want to put t versus like eta, I put omega versus s omega, which is same thing. I am just representing this in terms of a spectrum, or this time signal is represented in terms of a frequency signal over an omega. So, exactly the same time, you do not look at that. Let us say this black line is, I just drew this black line in a red pen. So, I have this, instead of eta I have here z with an amplitude ZA, instead of A I have ZA. So, I have exactly the same spectrum. In other words, what does it mean? It will imply obviously half of ZA square by omega. In other words, if I add this area up, I will end up getting essentially a quantity proportional to energy of this spectrum into rho g, because energy of any signal is proportional to half of amplitude square. So, this is a question of representing it. So, our question therefore is that given this, find this in a sense. Now you see there is such a one line procedure that will come out in a minute. So, what is this half Z A omega square by d omega? Okay. What I can write this, I think I will draw that in a bigger graph because this will take time. So, draw the red only. This is just bigger one to show you. So, I have, let us say this is S Z omega and I have this. And this part is, or rather S Z omega I can call it, is half of this, we know that, this is how we have done. Now, see here, this is equal to half of Z A by A, which is equal to, right, or rather we can write H because you see this half A by D, sorry, here A square, in this A square, right. So, you see this is, you understand that Z A by A is H omega, half A square by D omega is S omega. So, what is happening? It is become simply this into this. Look back at this. Therefore, this amplitude is this amplitude multiplied by square of this at the appropriate frequency. Straightforward. So, the procedure is as so simple that it is actually embarrassing in some sense. What I mean, therefore, the procedure therefore is something like that. Never mind the time signal, I have this spectrum S omega versus omega. Somebody has given me these H omegas. This is what we have done in regular wave. Remember that looks something like that. Take an appropriate place, say this and this same at omega, say I call this to be say A, I call this to be B. My responses become B square. A into B square, sorry, C is A into B square or S set omega H square omega into S omega. Okay. So, what is H omega? H omega Z amplitude of response at that frequency divided by A, that is nothing but this, because you are plotting, see remember here also we plot it. You can say it is a non-dimensional way of plotting it as if it is linear motion. Basically, you are plotting the output per unit input. because it is a linear response function. After all, if as I told you that for a given omega, let us say given wavelength 100 meter, if my heave was 2 meter for 1 meter high wave, then it is going to be 4 meter for 2 meter high waves, because a 2 meter high wave is 2 1 meter high waves together, both will give 2 plus 2 4. So, it is as simple as that. So, you see, now tell me, I have a formula for this, because we have discussed that last class throughout, this formula theoretical. I have got this discussed in the very first beginning lectures, how to get this, the transfer function. Let us, single degree of freedom, you have a solution, if you could solve it, whichever way, let us say this is given, this is in fact we will find out afterwards that the most complex part is this. This is where the hydrodynamics lies, this is where everything lies. This is a formula as on now. This is where hydrodynamics and everything lies, added mass, damping, various methods, and let us say you ended up, somebody gave it to you, either experimentally or determining it. How do I get this? If I know this too, this into square of this, one line of calculation. Okay. So, you see, that is why I keep saying that getting therefore that irregular motion, this picture from this picture is as trivial or as simple as this, but because it is but very important. Everybody in industry, everywhere you go, people are going to ask you that tell me the response in irregular waves, because actual oceans are irregular. If you go to actual ocean, nobody is going to find a wave like that unless you make it in a lab. So, therefore, when you go to an open ocean, any practitioner, any person will tell you, but you are taking sine bar. I never seen sine in my life when I sailed for 20 years in ocean. So, you see, the question is that people will tell you that how do you get this from this, but what we find out is that getting this from this process is 1% of the effort, getting this is 99, I will say 99.9% of the effort, getting this to this is 0.1% of the effort. But that 0.1%, if you did not complete it, it is like you didn't add the final spice on your like food, people will not understand. You have to finally give them this, not only this, filtered quantities from this, which I will come in a minute. So, you see, people are going to ask you, but you have to tell me how does the ship respond in CSAT 3, let us say. So, what would happen? You start with CSAT 3. So, I know H 1/3, I have a formula for this, then I have got this from a different source, I combine, I get, then I will say in CSAT 3 my heap motion response is this, spectrum is this. This is what is known as response spectrum. Now, you will, now having said that, we will find out that this spectrum also actually satisfies all the statistical quantities same as Rayleigh distribution, narrowband Rayleigh distribution. Therefore, we will be able to find out what is my average amplitude of the response, 1/3 amplitude of the response, and all quantities that I want, just like what I could do for this. See, here I could find out what is the most probable wave height in 1000 seconds. I can find out this also. What is the most probable roll, if it is roll angle in 1000 cycles or seconds. Everything is same, because this graph is assumed to be having same form as this. I will come to this in a minute, these formulas for that, but we can find out. This is what people will ask you, that tell me that my roll, average roll does not exceed so and so. You cannot tell peak roll, because average means certainly one can be high, but that is, we will come to that in a minute. There is a fundamental question. The question is coming back to this. You see here, I started with saying this line, body floating with 0 forward speed, this procedure, but actually ship is not 0 forward speed, ship is moving forward. Okay. So, now what happened? What changes happen because of that forward speed happens? This is, let us talk about that. Now, you see, we have seen that there is a ship here. You are standing here. Now, you see, there is a wave coming absolutely like that. But if you are standing here, you are going to see this wave coming and you are going forward, you will, to you wave will appear to be like that. Remember, the frequency will change. So, what would happen? The wave that this ship encounters are the encounter waves. Now, I have this spectrum. wave spectrum eta, which I broke it down to but the ship is not seeing this. The ship is seeing this as in other words, if this was omega 1, ship is seeing omega E1. If it is omega 2, ship is seeing omega E2. If it is omega 3, ship is seeing omega E3. Remember, the one that ship is feeling is not the omegas. So what happened when I broke it down this spectrum to this omegas, that is not what ship is responding to. So I have to one more step, I have to first break it down, then change this to omega E, then that I have to filter to this output. So that is why in forward speed I have this problem. So that means what I have to do is that, see, if I see in terms of spectrum, see I have this spectrum, wave spectrum. What does this mean? Say this is certain omega. Let me choose one omega I. What this mean? This means I have a wave which is this particular omega I. But now as far as the ship is concerned, the ship is going to see this here as, well, these are all sine curves, like it does not look like sine, but this is only for my handwriting problem. So it is going to look like omega EI. So what would happen? You see, I must transform this. So this is my S, what we call, this is my S omega versus omega. I have to transform it to S omega E. Well, you can call it SE omega E, 2 omega E. This should be my spectrum, whichever way it is, which basically is what my ship feels. In other words, basically the waves that I find out, you can say in this fashion, these waves that I find out are measured with respect to an absolute frame of reference. You have to transform that to a frame of reference which is moving with the ship, because you are seeing the same waves as you move. So in a sense it is nothing but transferring the same waves to a moving frame of reference. And obviously if you move at different speed, you will encounter the same wave at different frequencies. For example, if you went at the same speed of the wave, you would not even encounter, nothing is going to hit you. That we have seen, zero encounter. So I need to know this though. Now tell me an interesting part, what does this mean? This is this side, it is actually half of A square by d omega. Well, what is this area means? This area essentially means energy of all the waves of this frequency. Now you see, this frequency gets transformed, let us say omega E gets transformed to omega EI. Omega E gets transformed to omega EI because I know that omega E equal to omega into 1 minus omega V by G. This we know this from beforehand, encounter period. This formula we have done it before in our very beginning classes. If you look back the lectures, encounter frequency, frequency of encounter. We have done even problems, how, and if the formula looks like this, we have done this. So I know that this omega E, this wave of frequency so and so will appear as so and so. Now my next question is, how do I get this? What is my SE? This value, right? So my question is, how do I get this? Now you see here, this block should represent energy of all the waves of all the waves which are same as this, just that you are viewing it from a different reference frame. So energy will remain constant, energy cannot change. Whether you run and see the waves or you stand and see, same wave would have the same energy. So therefore this red block and this black block must be same area wise. Okay, this is where gives me the interesting point. So what is the red block? See, the black block, the energy is here S omega into d omega, whereas that is S omega, well, let me call it with a particular I, okay, or let me put it this way only. So, this must be same for a given bandwidth. Remember, I mean I just dropped this I because I is this thing. This is S omega d omega, this black, and this is S. So, I end up seeing this. So, now it is only a mathematical manipulation, we will just do that. So, now you see I have omega E equal to omega minus omega square V by G cos mu. So, d omega E, how much is d omega is coming? 2 by d omega, let us say 1 minus 2, that is right. And what is from this formula S omega E? You agree with that straight formula, this? So, this becomes so you see you get this formula here and you get this formula here. So, it is now a simple procedure to transfer the absolute wave spectrum to what is called an encountered wave spectrum, that is wave spectrum seen by the ship. How do we do that? Absolutely straight. Once again I do that. Every point see here, this any point at omega will transform to let me put this. Why this formula is something like that, and the height, this height will transform back to a height here. This height is going to be S omega E, what did we write, 1 by. So, what is happened now, you see, that means for each point I can get this. That is very simple, right, as far as calculation is concerned, S omega, and I am calling it S E omega. Okay. So, you see now let me, so what we call this we can call absolute this is the one that I got from the formula, this is the one that has been actually like obtained at a stationary point, etc., which is what the observers gave. This is same wave, same spectrum as viewed on board the ship. Obviously, this cannot be have a formula because it depends on V, it depends on mu, depends on in what angle in the waves and what speed you are moving. See why I shown this, a very interesting point I have to show in this transformation before I go any further. Look, cos mu in a head sea, that is when the waves are coming towards the ship, cos mu is within 90 to 180 degree. Let's say just simple case of head sea and following sea, 180 degree. What happened to this value cos mu? -1. So, this becomes larger, 1 plus. So, S omega is comes down, because S omega E, see this is more than 1, right. If this is more than 1, obviously this is going to be less than this. So, this value will come down, and omega E of course becomes more because this is negative, that means this gets stretched this side. So, it is something like, remember the area under this graph, net, what is the total area under this graph? The total energy of the waves, that must remain same. Obviously that is true, because if you integrate like if you simply integrate this and this 0 to infinity, the total energy remains same because component energy is same. So, there is no doubt on the area under that, and that is a fundamental principle, energy cannot change. But what is happened is interesting, that if I have a head C, it is getting stretched this side and the top is coming down. So, it is something like you are standing here and kind of pulling it. It is like you are standing and pulling it. So, there is a change in a head waves. But look at the following wave, which is going to be very complicated in some sense. I will discuss that in a minute. You see, let us take the straightforward case of cos mu to be 0, then my cos mu is equal to 1. What is happening? Number one is that this becomes less, or we should put this another diagram, because it is going to be, I will put in 1 only then. So now what is happening, if I want to get omega S omega E, now each point is getting pushed. Remember this formula, or rather shall we write this formula again here, or rather we can just transfer that. See, omega E is becoming less than omega, because my cos mu is equal to now plus 1. So, it is getting squeezed, okay, and S omega E is going to become more. That means as if I am pushing here and these things are blowing up. So, you see what happened, it is becoming something like, well, here only getting blown up. So, each point is getting pushed and getting blown up. Now, the most interesting point is that what happens, what would happen, remember there is a case when omega is equal to 0. Well, before that let us look at this. This becomes 0 at some point. What happens when it becomes 0? It becomes infinity, okay. So, it becomes 0 at omega equal to g by 2v cos mu. So, at omega equal to g by 2v cos mu, see this part becomes 0 at omega is equal to 2g, well, g by 2v cos mu, okay. At that frequency what would happen? You are going to find out that this thing has become infinity. So, actually this thing would have gone to something like infinity. After that what happens? You will find out, I will leave it to you to work out. After that what you will find out is that, see, omega E, if you increase more, begin to actually reduce down. That means omega E, although omega is going up, omega is goes this side. So, the graph becomes very interesting. It actually, if you work it out, it will become something like this. Let me draw here. This goes to infinity, then for the next domain it goes to minus infinity, then it basically goes like that and goes like that. So, the shape looks very odd, very odd, very different, because let me just put this in a slightly better perspective. Just let me put it in a little better perspective, because otherwise it may become little confusing in following C case part. I am going to draw this with respect to this formula for omega E, and if you recall, my formula looks like that and it goes like that, and this part happens to be omega 1, which is happened to be and okay, this is omega 1 g by 2v cos mu, no, and this part, or rather let me put it this way, omega S E infinity. Okay. Now if you take omega equal to G by V cos, that is this point, or rather let me call this as omega 1, call it omega 2, 0. Now the question is that when I do this transformation here, it like that at this frequency equivalent, this goes to infinity. We can just check it yourself. After that, see what is happening, my omega is increasing. See, this is my omega e, remember, this is my S omega e. See, up to this part, see omega is in, see I have this graph omega and omega e and S omega e. Now omega is increasing here to here. So omega is increasing here to here. At this point of omega equal to G by 2b cos mu, I have gone to omega e G by 4b cos mu, and S has become infinity. After that I am increasing omega further. What happened? Omega is coming down. So omega is coming down this side. And if you see the formula for S, it will become negative. So actually it invert to that and go, it will become negative infinity and begin to come down. We will come to that. I'll come to that. Physical significance is that you are actually going this way and the area becomes energy. See, if you take absolute value, you have to reverse it. The physical significance is very simple. When I integrate a graph in a cyclic way, it is the area under the graph that is physically important, that remains positive, because d omega become negative. You see, if I go, I will show that to you in a minute. So physically there is no contradiction if you use that way, but we normally use reverse. Now take this point. At this point what has happened? Omega is 0, so I come to this point. But after that, if I go further, I end up getting a graph like this. So I end up getting a graph like this. And what is now I'll answer your question. See what is happening, I am going this graph like that, going like that, going like this. Now if I want to, what is the energy on the waves? It is this area. So here if I take an energy, take from this point to this point, since I am traveling in a negative direction, I will end up getting the same energy. See, area will be positive. See, if I take a graph, something like this graph, if I go this way, you will always find the area, whether it is whichever way you do, you end up getting the net energy under the graph. So here when I go from here to here, see I have this energy. Now here when I go here to here, I have this to this, I will have positive energy because my d omega is negative, my S omega is negative. So I get positive. So of course this is very confusing. So what people will do is that you reflect this back. See, this is also very difficult. So what people will do, you will reflect this back on this graph. So you will say this is my zone 1 coming because of this part, that is I will call this as zone 1, this is zone 1. Then this 2 is this part, remember this part. So I can do that by reflecting that area wise this way. And 3 is this part which I can, because I am taking absolute value like that, I can reflect it back like that. So what would, this is becoming very confusing to you, but what would happen, you end up getting something like this, infinity, this is infinity. So what I do, this zone 2, zone 3, zone 1. This 2 I don't plot it this way because people always are confused. So what I do, I reverse it and make an absolute value just for the sake of plotting. So when I reverse it, I will end up getting here this zone 2. And I reverse this, I will end up getting zone 3. So this is my reverse zone 2, this is my reverse zone 3, and I add it all up to end up getting the graph.
So it should be symmetrical, zone 1 and zone 2?
No, not necessarily, not at all, not because that depends on the response. It need not be symmetrical at all.
So for an omega which is greater than say G by V cos mu.
G by V cos mu is this.
Omega E is tending to negative.
Yeah, that's.
Negative frequency means.
Yeah, that we have discussed long back in earlier. No, negative frequency essentially implies that you are moving faster than the wave. Therefore, wave would appear to be as if going receding. See, you are standing on a wave. See, it's like you are here, wave is here. Okay, I don't know how to give this demo here. So it's like you are here, wave is here. Now you go faster and wave is going like that. So, as a result 2u wave appears to be going on the other side. That is what is negative frequency, that we have discussed at length at earlier time, you know. See, that means physically negative frequency. See, it is like if you look at this graph also, a cos kx minus omega t, it implies a wave moving in plus x direction. But if I have a cos kx plus omega t, is minus or minus omega t, it is, this is actually minus of minus omega t, which means it is moving in the other direction. Same thing. Now, to you it appears to be moving in the other direction because they are going slowly. You have seen this relative speed in a train and everywhere, you know, you are passing fast, you think the other train is going backward. Same thing, exactly the same thing. Physically, though, both are moving forward. So, the physics, the dynamics involved is for forward. It is only that it appears as going backward. That is why we talk in terms of absolute, because just the question you ask, people have a difficulty of thinking in the negative side. So, here I have got negative omega I, negative d omega I, negative s omega. So, it is better to make it both positive. That is what is done. So, this is how, this is a very special case of what we can call wave spectrum in, you may say, in following waves, which becomes more complex, you know. Now, looking back to this part, you know, here if I were to look back to this, see, the interesting part that I want to tell people is like, you assume this way, you have a bar here, piston, head waves, pull it this side, pull it this side, so it becomes fat. Following waves, push it. Now, you keep pushing, at some point this will shoot up to infinity, okay, and then push farther, it will go on the other side. So, physically you think that way, you know, like it is very easy. I always, I am fond of telling this because you do not make a mistake in the shape. So, you know, like you pull that, the same graph, the area must remain same, like a wire here, it will just flatten down. Push up, you have a block here, you cannot go beyond that, it will go shoot up. In fact, you will find out later on that this is equal to, this infinity is equal to group speed. Group energy of the wave. In fact, it is very interesting. I tell you, this part, you remember that this part in resistance course, this will be equal to, you will find the group speed of the waves, which means the speed at which energy travels, and you will find out actually that this is a phenomenon of energy trapping, because I am surprised the approved didn't ask me what is the meaning of infinity, s going to infinity. What is meant by infinite energy, right? I thought you would have asked me, but the question is that energy is not this thing. See, energy is always, remember, this into this. So, this goes to infinity, but this goes to 0. You will find out that therefore, there is no mathematical contradiction. Otherwise, it's difficult to understand why, and in a program, computer program, you have to make sure you do not hit that point, because your program will stop under flow error. But there is no physical contradiction, remember. So, what you can do, other techniques, analytically integrate and all that stuff. So, anyhow, with that I am going to stop this lecture, and the next one we will now talk about the responses including this transformation, and then we will find out that for shape we are so lucky that if you encounter bad waves, you can simply change direction or speed and basically become better. With that, I will end this lecture.